Okay, hello there. That was some AC/DC for you by request, microphone, and today I'm going to teach you guys about inverse variation. And inverse variation, we did direct variation already in this class, and a quick reminder that that's got an equation of y equals kx, and inverse has its own equation as well, x times y equals k. And you should know that, memorize this one. It's a pretty easy formula. And from that equation, you can manipulate it. If I took this equation, the x times y equals k, and I divided both sides by x, I could get the second equation here, y equals k divided by x. Or if I took that same equation and instead of dividing by x, I divided by y, both sides by y, I'd get x alone. So these are really the same equation. All three of these are the same equation, just manipulated. So if you know the first one, you've got them all. Okay, so we're going to talk about the difference between direct variation and inverse variation. If it's inverse, it has to fit into this equation here. If it's direct variation, it has to fit into that equation there. So the first type of problem I'm going to show you is where I give you a table. Zoom in a little. And I give you x, y table, and I got 215, 4, 7.5, 10, 3, and last but not least 15, 2. So, I'm going to use that equation, the x times y equals k. So if I take these numbers, 2 and 15, I get 30. If I take 4 times 7.5, I get 30. 10 times 3, 30. 15 times 2, 30. So since these are all the same, that would be k. It is direct variation. Sorry, it's inverse variation. And the directions were, is it inverse? I forgot to write the directions. Is it inverse, is it direct, or neither? So in this case, it's inverse. And that's the answer. Okay, so that's the first one. Second one, determine which variation and write a function model. And once again, I got a table, x, y table. I got 210, 4, 8, 10, 3, 15, 1.5. Okay, so if it was inverse, I multiply the x times the y, and I'll get 2 times 10 is 20. 4 times 8 is 32. 10 times 3 is 30. I got a problem. Those are not all the same numbers. They have to all be the same thing. Otherwise, it's not inverse. Let's see whether it's direct. If it's direct variation, then I'm going to take, y divided by x equals k. So if I take 10 divided by 2, that better be the same as 8 divided by 4, which better be the same as 10 divided by 3, which better be the same as 15 divided by 1.5. So that's 5, that's 2, this is not going well, 3.3, So that's not direct variation either, because these numbers are not all the same. They all have to be the same. Therefore, it's neither direct or inverse. Okay? Since it's neither direct or inverse, I can't come up with a model for it. Otherwise, I'd come up with an equation. All right, same directions, number 3. And this time my table is like this. 0.2, 40. 0.5, 16, 1.08, and 2, 4. Okay, so if it's inverse, then I'm going to take x times y and it should equal k. Constant of variation, same thing. Constant is a regular number. So if I take 0.2 and I multiply it by 40, I get 8. 0.5 times 16 is 8. 1 times 8 is 8. 2 times 4 is 8. So this is inverse variation. And I can write an equation for it. K equals 8, because that's what all of those are. Notice I did them all. If one of them is not 8 and all the other ones are, it's not inverse. Okay. So my equation or my function model would be x times y equals 8. And that's the equation. Okay. Finding k is the name of the game. That was the name of the game when we did direct variation as well. Okay. So that was number 3. Moving on to number 4. X, same directions. Point 2, 8, 0.5, 20, 140, 1.5, 60. And let's see, if I take inverse, if I multiply them together, and suppose I take 0.5 times 20, half of 20 is 10, 1 times 40 is 40. I got a problem already. It's definitely not inverse. Let's see if it's direct variation. So if it's direct variation, then it's going to be k equals y over x. So if I take 8 divided by 0.2, if I take 20 divided by 0.5, if I take 40 divided by 1, and 60 divided by 1.5, what do you get? In this case, I'm getting 40, 40, 40, and 40. So it is direct variation. And the equation is, there's a couple of them. Usually I go x, y equals 40x. That's certainly not the only one. Since we use that other equation, you could go 40 equals y divided by x. That's another good one, okay? Either one of those is fine. If you have questions, please bring them to class. Number 5. Suppose x and y vary inversely. and x equals 4 and y equals 12. What function models the inverse variation? And B, what is y when x is 10? Okay, so first, I'm going to take my inverse variation equation. Nice to have that. X times y equals k. And I need to find k. So they told me x is 4 when y is 12. So k equals 48. And now I can come up with the equation, the model, which would be x times y equals 48. And that's part A. Now that I have that, I'm going to use that down here. And I want to know what y is when x is 10. So if I take the 10 and I pop it in there and solve for y, I get my answer. Okay, if I just divide both sides by 10, I get y equals 4.8. Okay. Number 6, once you try this one. Suppose x and y vary inversely. And x equals 8 when y equals -7. Same kind of directions. A. What function models the inverse variation? And B. What's y when x is 2? Okay, so why don't you pause and try this out and then come back. Okay, so first, x times y equals k. X is 8, y is -7, k equals -56. So my equation is x times y equals -56. Take that to the second part. And I'll pop in the 2 for the x. Divide by 2 and get my answer, y equals -28. Okay. 7. Your math class picks up litter at a local park. Each week, the amount of litter is approximately the same. And the table shows the number of students and time needed for the pickup. Okay, and here's my table. I got number of students. Down here's time in minutes. I got 3, 85, 5, 51, 12, 21, 17, 15. Okay. And I got a couple parts here. A, what function models the data? And B, how many students should be needed to complete a 30-minute pickup? Okay, so back to this. All right, so if I start with, inverse variation, that means x times y might equal k. That's what I'm hoping for, okay? So, for example, if I take, you could start by dividing. It's either dividing or multiplying. If I went 85 divided by 3, what's that? If I went 51 divided by 5, what's that? If I went 12 divided by 21, what's that? Okay, so you can see if I divide this one out, I get 28.3. And if I divide 51 by 5, I get 10.2. Yeah, it's just really not working very well. So I'm going to scratch the direct variation idea. That would have been dv. Let's try the other way. If it's inverse, if I go x times y, what is 85 times 3? What is 5 times 51? What is 21 times 12? And last but not least, if I multiplied 17 and 15, you're going to start to see a pattern here. $85 times 3, I get 255. 5 times 51, I got 255. 12 times 21 is 252. And 17 times 15 is 255. Okay, so those are real close. And what you're going to find is this is a real world kind of problem. Nothing ever comes out perfect in the real world, okay? So I know this number, the 252, is slightly off, but it's real close, right? Which means if I was to take my model, this really is a good model. I'm going to use the 255 because there's 3 of them there, 3 out of 4. They're real close. If that one was way different, then we might have a problem. But that's really pretty good, especially for the real world. Believe me, nothing works out perfect in the real world when you're looking at data. So that's my equation that I'm going to use for the model. What function models it? Okay, and now that I have that, I got, x and y. I know x is Actually, it could be either one. X could be the 3, or X could be the number of students, rather, or the amount of time. So once I've got this, X times Y equals 255, and I want to know how many students. If I plug in 30 for X, or 30 for Y, you'll get the same answer. When I divide it out, divide by 30, you get X, or Y in this case, is about 8.5 students. So I'm going to say 9 students. Tough to have 8.5 kids. You can all make that joke about the short kid if you want, but anyway, about 9 students. Okay, so there's your answer, and I'm done with that. Questions so far? If you have them, please write them down. The last thing I'm going to show you is I'm just going to start to introduce this, because we're going to get more into it in the next chapter here, where I'm actually looking to get into the graphing calculator. I want to start showing you a hyperbola here, and it's if I graphed y equals 1 over x, what does that look like? So if I type that into the graphing calculator, y equals 1 divided by x, you get this, okay? And this is a hyperbola. It's got 2 asymptotes. I'll write that word down for you so I can spell it correctly. And remember, an asymptote in this case would be like the x-axis or the y-axis, because these 2 curves, they approach that axis but never actually get there. You know, the equation is 1 over x, which means x can never equal 0, right? Because that's undefined. Nor will I ever get y to equal 0, because I can't get 1 over something to equal 0 either. Which means it's got 2 asymptotes. If I was to ask about what the domain is, the domain would be x is greater than 0 or x is less than 0. Or you could say all real numbers except x equals 0, because there are values for all x values except for that one right there, x equals 0. The range would be exactly the same, except you're talking about the y values, where y would be all real numbers except y equals 0. Okay, so that would be the domain and the range, and that's what that graph looks like. Okay, so if I go back over here for a moment, and I just write down, an asymptote, asymptote, is a value that a curve approaches but never reaches. And that was the name of that shape that we just saw, the hyperbola. Okay. And I'm going to stop there. Thanks for all for watching. See you soon.